subject at hand. So basically, I'm by training an electrical engineer, but past 38 years, I've been working only in the area of energy audits, mainly industrial energy audits. So as you know, in energy audits, one ends up being a mix of everything. One is an electrical engineer, a thermal engineer, a mechanical engineer, and also partially a chemical engineer, because it's an interdisciplinary field and one needs to know a little about everything to come up with some reasonable suggestions which can help our clients. Yes, over the years, I had the opportunity to do a lot of work in India and also outside. So this particular session on vacuum pumps, I will be just sharing my thoughts and experience on this particular area. I always found it one area which was a bit difficult for energy auditors, mainly because of the lack of sufficient information and the limits on the amount of measurements which we can take on the field to assess the performance of these systems. So I thought this would be an interesting 45-minute talk, sharing some basics about vacuum systems and also a few case studies. Time is quite short to get into very great details, but possibly we can just, I'll just throw a few things at you, and maybe towards the end, we'll also probably have a few minutes for some discussions. And along with your queries in the end, I would also request some of you who would have good experience in these systems, because I don't claim to be a specialist in vacuum systems. It is just one of the many areas which we study during the energy audits. So let's get started without wasting any more time. Let me just share my screen and get started. Firstly, is the screen visible, and am I audible to everyone? Is my screen visible, and am I audible?
You are.
Okay. So let's quickly run through some of these slides, and I'll keep telling my stories as we move on. Now, vacuum systems have been a bit of an esoteric area for most engineers, for reasons that unless you have good instrumentation on the field, it's really very difficult to know exactly what's happening. That is one of the major lacunae in vacuum systems, that the instrumentation usually is bare minimum, which is required to operate the system. Usually, other than a few pressure gauges, one really does not have much information on how much of gases the vacuum system is evacuating, or we do not have much idea about the amount of energy which is being consumed. Okay, so there are a lot of issues which makes this field a bit troublesome for energy analysis on the field. And before we get down to some of those issues, it's always helpful to look at the history of these vacuum systems, where it all started and what are the main areas where these are used. Now, one of the major applications of vacuum systems in the industrial arena is the evacuation of gases from processes. Okay, chemical industries, petrochemical industries. Okay, where there are a lot of chemical processes happening, where you need to maintain the pressures in certain systems at a certain level. You need to evacuate vapors and gases from the system. So that is one of the major areas where vacuum systems are used, where the consumption of energy in these vacuum systems is also quite significant. But as I said, the amount of practical information available on a site usually is very, very limited. Vacuum systems are also used in other industries. Packaging is one industry where, especially in food and pharmaceuticals, evacuation of the uh, the containers before the material is charged into the container is a very common application. Vacuum is also at times used for transportation of polymer chips, powders, and so on. In again in various kinds of industries, especially pharma. In the engineering industry, vacuum is used for gripping of components, especially with such a huge amount of automation and robotics coming into play. And of course, finally, the crudest use of the vacuum system is for cleaning, which all of us are familiar. Most of us would be having vacuum cleaners at home. Here, the focus of this talk would be mainly on the industrial applications and more toward the continuous process industries, or maybe not really continuous, maybe semi-continuous, or maybe even industries with batch operations, but more towards industries which are using sizable amount of energy for their vacuum systems. In industries like engineering and certain other areas, usually for example, pharmaceutical formulations, etc., vacuum systems do exist, but these are generally a small portion of the total energy consumption. So we are looking at some of the big consumers and also trying to see what possibilities exist for reducing energy cost in these vacuum systems. Now, the word vacuum originally is derived from Greek. It seems it means empty. Okay, so when you say vacuum, the pressure in your system is below atmospheric pressure. So essentially, you're evacuating the molecules of air or whatever other gases which may be there in a particular system and throwing it out. Okay, and finally, when there is nothing left, okay, you reach a level which is called as ultimate vacuum. Okay, but ultimate vacuum generally is never reached. Okay, and it's almost impossible to reach ultimate vacuum. Can come very close to it, but never reach that final value. And it seems that vacuum pumps existed in some rudimentary crude forms even in the first century BC. But yes, mankind always has been playing with whatever has been lying around and trying to innovate. So it is not surprising that even before Christ it existed. But the real discussion and research on vacuum, it seems, began during Galileo's time. Okay, this is the 17th century. Okay, Galileo is the first person to document that a suction pump which works on atmospheric pressure cannot lift water more than 10 meters. Okay, all of us know that 1 kg per centimeter square, or approximately 1 bar, is equivalent to 10 meters of water column. Okay, that is the absolute atmospheric pressure. And subsequently, one of his disciples, Torricelli, uh, he is the person who discovered that atmospheric pressure is equal to 760 millimeters of mercury column. And today, those of you who have at any point of time dealing with vacuum systems know that the unit of vacuum, which is most commonly used, is torr. Okay, 1 millimeter of mercury column is 1 torr. And subsequently, there have been developments. 1650, Guericke inventing the first mechanical air pump. 1825, Dumas use steam to displace air out of a vessel. So possibly he's the forerunner whose work probably inspired today's steam ejectors, which are very, very commonly used for vacuum applications. Uh, and subsequently, Bunsen came up with the concept of using a jet of liquid for evacuating gas, which again is a very commonly used kind of vacuum pump these days, usually with water, the water jet vacuum pumps. In spite of this very long history of which is associated with vacuum science, uh, even today, even some of the people who are accomplished experts in the field of vacuum science and engineering say that it is more of an art than a science to make a vacuum system actually work practically for any application. Okay, and probably the most difficult applications are in the industry, especially in the process industries, which are handling a lot of a mixture of a lot of gases, where the composition of the gas is also often not completely known. So getting the vacuum levels with a reasonable amount of energy consumption, and also evacuating the gases in a manner by which it can subsequently be processed, is a real challenge. Okay, and for people like us, energy auditors, who are basically not scientists, not really engineers who are giving birth to any new technology. Okay, I always say that the energy auditors are not gynecologists. We don't give birth to life. Okay, but we are basically post-mortem specialists who, after things are not working too well, go and do an analysis and then try to say that this should have been like this, and then try to make improvements. Okay, so for ordinary mortals like us, probably vacuum engineering is neither a science nor an art. It is black magic. Okay, we are always mostly groping in the dark, trying to get some information by which we can make some small intervention to get energy savings in these systems. Understanding vacuum, since many of you may not be dealing with vacuum related issues in your daily work, I'll just introduce some basic terminologies here, so that one is comfortable as we move on. Okay, now when we say vacuum, obviously the pressure in the system is below atmospheric pressure. Okay, so here, if you take a look at the screen, okay, 760 millimeters of mercury column, or 760 torr, okay, is the absolute atmospheric pressure. Okay, and ultimate vacuum is 0 torr, the other extreme. Okay, as I told you, ultimate vacuum cannot be achieved. Okay, we are living somewhere between atmospheric pressure and the ultimate vacuum level, which is 0 torr. Okay, now depending upon what kind of process we are dealing with, the vacuum levels can be quite different. Okay, and the kind of devices or equipment which we have to use to achieve those vacuum levels also would be different. Broadly, vacuum pressure ranges are defined as rough or low vacuum, which would be anything from 760 torr going down to about 0.75 torr. That range is called as rough. Fine or medium vacuum would be 0.75 torr all the way to 0.0075 torr. High vacuum would be again from 0.0075 torr going all the way to 7.5 into 10 raised to minus 7. Okay. Actually, there, I think there's a small correction to be done on the slide. It is into 10 raised to minus 7. Okay, it is not 7.5 raised to minus 7. Small correction there. Okay. Ultra high vacuum would go all the way from 10.5 into 10 raised to minus 7 all the way to 7.5 into 10 raised to minus 11 torr. And extremely high vacuum is 7.5 into 10 raised to minus 11 torr. Okay, very, very low vacuums. Okay. Now, ultra high vacuum and extreme high vacuums usually are used in laboratories and in certain high-tech fields like space related manufacturing, semiconductors, and so on. Okay, usually for industrial applications, most of the applications would fall into the rough vacuum to the high vacuum category. Now, some of the important terminologies which we should be familiar with, one is the evacuation rate, or which is called by vacuum engineers as gas pumping speed. Okay, it is not really the rotating speed. It is the amount of gas which is being evacuated. Okay, it can be meter cube per second or meter cube per hour, depending on what kind of units one is using. Okay, so evacuation rate is how much amount of gas is being evacuated by the vacuum pump in a certain defined period of time. Usually it will be a second, a minute, or an hour, something like that. Ultimate pressure is the lowest pressure, okay, or the highest vacuum level that a vacuum pump can achieve. Okay, as the vacuum pump approaches ultimate pressure, its evacuation will drop to zero. As I told you that zero torque, okay, can never be achieved. Okay, but as a vacuum pump starts evacuating the gas, the pressure in the uh, vessel which is being evacuated will keep dropping. Okay, and as the pressure drops, the amount of evacuation also drops, as we will see later. The operating pressure is the actual pressure at which finally the system stabilizes. This would depend upon the capability of the vacuum pump and also the amount of gases which are being produced on a continuous basis in the process. Okay, so ultimate pressure is the lowest pressure which the vacuum pump can achieve. Okay, and once it reaches the ultimate pressure, the vacuum pump is actually evacuating nothing. It may be operating, but its evacuation is very, very close to zero. Okay, it has reached its highest evacuation the capability is happens when the ultimate pressure is reached. This curve shows us that on the right hand side you have 760 torr on the x-axis. Okay, now vacuum pumps usually are specified for evacuation at atmospheric pressure. Okay, so if a vacuum pump has got a capacity to evacuate 100 meter cube per hour, it will be at atmospheric pressure. As it starts evacuating, what happens is that the pressure drops in the vessel, reactor, or whatever may be the container from which the evacuation is taking place. And as on the x-axis, you have got the evacuation or the pumping speed. Okay, so a vacuum pump will give 100% of its capacity at atmospheric pressure. Then as it starts, the pressure in the vessel starts dropping, the evacuation capacity keeps on dropping, and once it goes below 7.5 torr, there is a drastic drop in the amount of gases which it can evacuate out of the vessel which is being evacuated. And that is understandable, even physically, because initially when it's full, there are a large number of molecules of the gas. As you keep on evacuating, the number of molecules keep on dropping, and the internal space within the vessel is highly rarefied. Okay, only few molecules left. So as you try to pull the last few molecules out, okay, the vacuum pump's capacity, it keeps doing work, but the capacity to evacuate is drastically lower. Now there are different types of vacuum pumps which are used. Okay, if you look at this particular chart, okay, on the extreme top you have the diaphragm pump. Okay, which is a small capacity vacuum pump, uh, which is basically diaphragms which are having some kind of a reciprocating action. Okay, diaphragms may be mechanically moved either with a piston, or it may be moved with compressed air, okay, or with some hydraulic fluid. Okay, so as the diaphragm keeps on reciprocating, it keeps on sucking air from the vessel and throwing it out. Okay, these are generally used for small applications. Okay, usually in laboratories or very, very small applications. Okay, not really on a large industrial scale application. Then you have the liquid ring vacuum pump, which is popularly used, okay, and is one of the workhorses in the industry. Okay, usually it comes as a watering vacuum pump. Okay, we'll look at how it looks like and how it works a little later. Okay, you have something called as a liquid jet pump. Okay, normally the diaphragm pumps and the liquid ring vacuum pumps, okay, and many other pumps which are listed here, the rotary plunger pump, the piston pump, okay, the scroll pump, the screw pump, the rotary vane pump, okay, the rotary piston pump, okay, roots blowers, okay, all these things come are basically positive displacement equipments. Okay, where a solid part or a liquid part is moving. Okay, in the process it is displacing gas and evacuating some vessel or chamber. Okay, a liquid jet pump is not a positive displacement pump. It is basically a liquid jet at high velocity, okay, which uses a venturi, okay, to create low pressure to suck out gas from a vessel. Okay, Similarly, if you go further down, you'll see the vapor jet pump. Okay, in its most popular form, it is what is called as a steam ejector. Okay, so steam ejectors and liquid jet pumps, that most commonly water jet pumps or water ejectors. Okay, so these are pumps which basically use the high velocity of a fluid to entrain gases which have to be evacuated. So the principal operation is slightly different. But the liquid jet pumps, the vapor jet pumps in the form of steam ejectors, and the liquid ring vacuum pumps are the most commonly used vacuum pumps for industrial applications. Then you have certain specialized pumps which also have been in existence for a very, very long time. Okay, the diffusion ejector pump. Okay, the and another pump which is called as a diffusion pump, a turbo molecular pump, ion sputter pump, cryo pumps, etc. These are highly special pumps. Again, not new technology. They have been in existence for a very, very long time, but which are used for very small evacuation capacities and for getting very, very low vacuum. These are maybe used in for laboratory applications, okay, in research, okay, and also certain high-tech industries like semiconductors, space, and maybe manufacture of uh, aircrafts and so on for certain material science requirements, okay, but not commonly used in the industry. So we are not really going to talk about it. But these have the capacity of getting very, very low vacuums, okay. In fact, the pump which can give the lowest vacuum is the last one, the cryo pump. Okay, the cryo pump, just for your interest, uses liquid hydrogen and liquid helium to generate vacuum. Okay, and along with liquid nitrogen cooling of the entire vacuum pump. Okay, so these are since they are not used in a very big way in the industry, we will not spend time on those. We'll mainly look at the pumps which are very popularly used and some of the new evolving technologies which probably can help us save energy in vacuum systems, which is our primary objective. Uh, Here, the diaphragm pump, the scroll pumps, the screw pumps, rotary vane pumps, rotary piston pumps, liquid ring pumps, roots pump. Here we are given the evacuation capacities, okay, normally available, okay, and as developments take place, usually most of these pumps are available in larger and larger capacities as time passes. But these are the usual ranges in which it is available, okay. So if you look at the evacuation capacities, the last two, the liquid ring vacuum pump, okay, and the roots blower, okay, or the roots pump, okay, the twin lobe blower pumps or blowers are very, very commonly used in industry because of the large capacities and the reasonably low vacuum which these equipments can give, which are sufficient for industrial applications. Okay, and other than these, if you go look at the other specialized pumps, they are all below here. In among the specialized pumps, there is only one pump which is of interest to us: vapor jet pumps, which, as I mentioned, comes in the form of a steam ejector usually in the industry, which also has got a good evacuation capacity, which is useful for an industrial scale operation. So the popularly used vacuum pumps, reciprocating pumps, rotary vane pumps. Okay, we'll take a look at it. Rotary vane pumps are also used in industry on a very large scale, more so in the non-process industries. Okay, where there are no chemical process involved. Okay, mostly rotary vane pumps are used in engineering industries and certain applications where basically the gases which are being evacuated are reasonably clean. Okay, because these are lubricated with oil and too much of contamination is not permitted in rotary vane pumps. Screw pumps are also like the screw air compressors which we are so familiar with. Okay, they are similar kind of equipment which are used for vacuum duty. Liquid ring vacuum pumps, I've already talked about. We'll see the pictures and how it works immediately in the next slide, perhaps. Roots blowers also, we'll see what it looks like. Claw pumps, okay, These are the screw pumps and the claw pumps. Okay, these are available as dry pumps without lubrication. Claw pumps have come on the scene relatively recently, in the past decade or so. Okay, and both the screw pumps and the claw pumps are today challenging most of the other kind of vacuum pumps from the energy efficiency viewpoint. Okay, today if you're able to accept the reciprocating pump is in fact quite efficient. Only thing, uh, people do not like it very much because of the wear and tear. Okay, because in a reciprocating pump, the piston movement creates wear and tear of the piston rings. Okay, uh, failure of all the valves and so on, and requires frequent maintenance. Okay, the rotary equipment and the liquid ejectors and the steam ejectors, these are much more rugged equipment, and industry finds those equipments more reliable compared to reciprocating pumps, which need a huge amount of maintenance. Now, the screw pumps of the dry variety and the claw pumps of the dry variety both are now challenging the other kind of vacuum pumps which are being used. And today, both these pumps, screw pumps and claw pumps, are of interest to energy auditors, because wherever it is possible to replace the other pumps with this kind of pumps, because they can give a reasonably low vacuum, especially in the rough to medium category, uh, it becomes a strong candidate for replacement, provided that the gases which are being evacuated uh, are able to work in these pumps uh, in a manner by which it does not lead to problems related to maintenance and reliability. What I'm trying to say is that most of the pumps which are lubricated, okay, or which have got some liquid which is involved, for example, the liquid ring vacuum pumps has got usually water or oil, okay, which works like a liquid piston. So this liquid also absorbs the heat of compression in the vacuum pump, because vacuum pump is also essentially a compressor working in the reverse. So whenever there is compression, there is mechanical heat generated. There may also be certain vapors which condense within the vacuum pump, so that latent heat also comes in. So all that heat which is generated, the mechanical heat as well as the latent heat, has to be removed from the system by cooling. Okay, in the case of a reciprocating pump or a vane pump, okay, it has to be removed by cooling. Okay, even in the other things like liquid ejectors and steam ejectors, the same problem is there. In steam ejectors, okay, the steam, which is the motive fluid itself, has got its own latent heat. Okay, so once it does its vacuum duty, it has to be condensed. Okay, and that heat has to be dumped on a cooling tower. Okay, in a liquid ejector also, the liquid has to be cooled so that the mechanical heat of compression and any latent heat coming from the gases which are being sucked out is removed. Okay, so the temperatures in these pumps have to be maintained at a reasonable level. Okay, and no overheating is permitted. In the case of the screw pump and the claw pumps, which are dry, they run at high temperatures. Okay, so because they work at high temperatures, okay, the chances of any of the gases condensing inside or polymerizing inside these pumps is lower. Not that it doesn't happen, but it is lower. So for many applications which are not very dirty, when I mean dirty, I don't mean that the gas is dirty and it's some kind of an effluent. No, the gas may have good value which has to be used in some subsequent process. Okay, what I mean is that, for example, claw pumps and screw pumps, okay, the temperatures inside the pumps may be on the upper side of 150 degrees centigrade. Okay, so at those temperatures, if any of the constituents of the gas which is being evacuated, if it has got a tendency to condense, okay, then you cannot use a screw or claw pump. Okay, if it is able to pass through at that temperature, then these pumps can be considered. Similarly, there are certain constituents, okay, especially in the petrochemical industry, which tends to polymerize at certain temperatures. So once again, we have to ensure that the temperatures which are prevailing in these dry pumps are higher than the polymerization temperatures of some of the constituents of the gases which may be evacuated. Okay? So there are a lot of issues involved in this. Yet, if you look at efficiency, okay, if I have to, if today, if I don't bother about any other parameter, and if I say that I'm looking only from the viewpoint of energy efficiency, then the dry screw pumps and the dry claw pumps would be the pumps of choice. Okay, we'll come back to these as we look at some of the case studies. And vacuum pumps are used standalone as a single pump, or multiple pumps may be put in stages depending upon the kind of vacuum level one requires. And again, you may have different kinds of pumps going into a combination. You can have a steam jet ejector working along with a liquid ring vacuum pump in series. You may have a steam jet ejector working along with a rotary roots blower, or a liquid ring vacuum pump working along with a rotary roots blower in series. All kinds of permutations and combinations are possible depending upon what is the final vacuum level which you require. And also, it also depends to some extent on the kind of gases which you're evacuating. These are the pictures of the various kinds of vacuum pumps. The reciprocating pump, I think everyone understands. Okay, it's a piston moving inside, sucking gas out. Everyone knows that. It's a positive displacement pump. Sliding vane pump is also a positive displacement pump, where the gas is sucked and discharged out, okay, by lot of vanes which are sliding inside inside an eccentrically located rotor. Okay, so as the rotor rotates, okay, the vanes will slide in and out. Okay, there is a spring which is supporting uh, the vane, so the vanes can move in and out. So where the volume is large, that is the port where the gases will get sucked in. It gets trapped between two vanes, and as it moves ahead, it gets compressed and eventually gets ejected out to at atmospheric pressure, or whatever is the downstream pressure which is there at the vacuum pump. Okay. This also is positive displacement. Liquid ring vacuum pump is actually a rotary pump. Many people feel it's a centrifugal pump. It's not. It's a positive displacement pump, where again there's an eccentrically located vane, which and there is water or oil inside this pump. You may also have glycol or alcohol, depending upon what kind of application you're looking at. And when this vane rotates, it throws the liquid to the periphery. Okay, and if you see over here, okay, it again creates a crescent moon like space, wherein the volume, as there are areas where the gas can get sucked in, get trapped between two vanes of this impeller, and as the vane rotates, the volume will keep on reducing, and finally it gets compressed and it will come out as gas at atmospheric pressure. Okay, so you have vacuum at the suction and atmospheric pressure at the discharge. Okay, now why do you say that it's a positive displacement pump? Because the water or the oil which has been thrown to the periphery works like a piston. So it is actually a liquid piston pump. That should be the real word for this. Okay, so this also falls into a category of positive displacement pumps. And liquid ring vacuum pumps are also very commonly used in the industry. It's a workhorse. Okay, in all kinds of industries, and especially in chemical and petrochemical industries, good number of these vacuum pumps are in use. Okay. Again, they can give vacuum levels which are in the medium to uh, uh, rough levels. Okay. Roots blowers or roots pumps are twin lobe blowers. I think most people would be familiar of this equipment, at least when it is used as a blower. Okay, again, a positive displacement equipment. It's a simple device. Okay, uh, to the blowers rotating in a manner by which air will get air or gases would get sucked at one end and get discharged out at atmospheric pressure. Okay, roots blowers again usually are used along with some other kind of vacuum pump. Standalone, the roots blowers do not have very great capacity to develop vacuum, but when it is working along with a liquid ring vacuum pump or along with a steam jet ejector, it is a useful equipment. The screw pump is again like of the screw compressors, which we are quite comfortable with in the compressed air game. Okay, these screw pumps are also basically screw compressors. Okay, which are evacuating quite similar to the way an air compressor works. Okay, the claw pumps, okay, are again uh, they have two claw-like impellers. Quite looks a bit similar to the roots pump. Okay, but these are different in the sense that these are the claws in the twin claws which are there in this pump are designed with very fine tolerances. Okay, and they are able to evacuate a huge amount of gas. Okay, and generate very low vacuum levels and work in a very reliable manner. So the screw pump and the claw pumps are the pumps I'm drawing attention to. So these are the pumps which today have the ability to give you reduction in energy. Okay, evacuate a good amount of gas at an industrial scale. Okay, and also generate low vacuum. Okay, but because the tolerances are very fine both in the screw pump and the claw pump, okay, the quality of the gas is important. Okay, uh, the pharmaceutical industry is slowly moving towards this. Okay, because uh, in many of their processes the gases which are being evacuated are reasonably clean. There is no chance of any polymerization or condensation taking place at the kind of temperatures prevailing in both these pumps, because the temperatures are high in these pumps. Okay, even in certain chemical industries, uh, people have now started experimenting with these kind of pumps, and the energy savings are so great that in some cases, even with minor reliability issues, people are keeping more spare pumps so that the pumps can be staggered. The operation can be staggered in a manner by which some spare pumps are always available, so that the existing working pumps can be stopped for a certain amount of time for maintenance and cleaning. Okay. Uh, we'll see some case studies on the kind of cost savings which are possible with both these kind of equipments. Now, coming to the other two kinds of pumps, which are again used in very large numbers. One is the liquid jet pump. Often it is used with water, so it is usually called as a water jet pump or the water ejector pump. Okay. Now, here again, these pumps are very rugged. Okay, essentially, there is a pump which provides either water, oil, or any other fluid, which comes at high pressure here. Okay, and it passes through the nozzle and it expands, generating high velocity, and the venturi. Okay, it passes through the venturi and expands to the diffuser of the venturi. Now, the venturi action results in vacuum being generated and in the high velocity zone, resulting in gases which are to be evacuated from a process vessel, okay, getting entrained with the motive fluid, passing through the venturi and coming into a tank where the water or the oil or alcohol or glycol, whatever is the motive fluid, will separate out, and the gases can be thrown out into the atmosphere, or it may go for further treatment in a scrubber or whatever it is. Okay, this is also a very rugged device and is used very effectively. And the most commonly used vacuum system in the industry, especially the process industry, chemical and petrochemicals especially, and also pharmaceuticals and food industry and so on, is the steam jet ejector. Okay, here steam is the motive fluid. Okay, again, it passes through a nozzle, generates high velocity through a venturi and out. Okay, again, like a water jet ejector, it creates vacuum in the high velocity zone. The process gases get entrained, and along with steam, it goes out of the ejector and into a condenser. Okay, where the steam as well as any other condensables which are there in the gas, okay, the vapor will condense out, and the non-condensables will be discharged out of the system. Okay. Now, when you look at the uh, vapor jet ejector, or in its most common form, the steam ejector, and you compare that with the liquid jet or the water jet ejector, okay, uh, the water ejector is more efficient than the steam ejector. Okay, the reason being is that water is a non-compressible fluid. okay, and steam, being a gas, is a compressible fluid. Okay, so when you're dealing with uh, a non-compressible fluid as the uh, motive fluid, or in the other examples which we saw, okay, where there is a solid or a liquid piston-like movement taking place which is pushing the gases, all those are more efficient, okay, compared to the steam jet ejector. So this is the uh, vapor ejector or the steam ejector, okay, where you have the motive fluid, okay, which is coming in, okay, entering a venturi and going out. This is the area where vacuum will get created because of the increase in velocity of the motive fluid when it comes at a high pressure and the pressure suddenly drops. Okay, the velocity increases significantly, vacuum is created, and gases get sucked in. And then it passes through the venturi, and as it passes through the venturi, and when its area reduces, okay, the gas along the gases, the motive fluid along with the gases which are getting sucked in will again get compressed, okay, and finally when it will passes through the diffuser, okay, where the velocity again reduces and the pressure again builds up slightly to the level of the atmosphere, because this is the high pressure zone and this is the low pressure zone. Okay, the point from where we are evacuating the gases is low pressure under vacuum, and this has to reach the atmospheric pressure or the pressure of the downstream stage. As I told you, it is possible that you may have multiple steam jet ejectors or water jet ejectors working in series or in a multi-stage configuration. Okay, so that's how the system uh, operates. Another important point in vacuum systems, especially steam ejectors, is that, as I mentioned, now here is the vessel where you need the vacuum. Okay, now this is a three-stage ejector. There is one ejector here, another one here, another one here. Okay, ejector, there is a condenser. Okay, what is the job of the condenser? To condense out whatever steam has been consumed here, the motive fluid. Okay, it has to also condense out automatically some other vapors which probably will condense at that temperature, and the non-condensables will move to the next stage where again you have steam coming in. That steam also gets condensed and the non-condensables will move further ahead. Okay, so when you need lower and lower vacuum, you have to go in for multi-staging. Okay, you may have 3 or 4 steam ejectors in series as a multi-stage ejector, or you can also have a combination of 3 steam ejectors with a liquid ring vacuum pump as the last stage, all depending upon what kind of vacuum you're targeting and what is the level of evacuation of gases that one is uh, attempting to do. Now, when you compare, as I told you, the steam ejectors and the liquid ring vacuum pumps are the workhorses of the industry, especially the continuous process industry and the semi-continuous process industries, especially industries which are having some kind of chemical reactions and so on. The advantage of steam ejectors is that there are no moving parts. It's static equipment, very, very reliable. Okay, lower maintenance costs. Okay, it can be sized for very large flows and lower pressures. Capital cost is not great. It is inexpensive compared to the other kind of vacuum pumps. Can produce low vacuum levels, which are required for many of the chemical processes. Available in a very wide range in terms of capacity and pressure capabilities. Okay, and when I say pressure capabilities, it is coming through multi-staging. Okay, the drawbacks is that the motive fluid can often be quite expensive. And today, why we are probably having this talk is because, as I told you, steam jet ejectors are very, very commonly used. And today, the price of steam, earlier, even when the price of steam was low, okay, still it made more sense, and electricity was expensive, still it made sense to go in for the electrical vacuum pumps, okay, which are operated through using electricity. Today, the issue is much more urgent because the cost of steam has risen very, very significantly. Okay, especially when you look at in the Indian context and also in the international context. the cost of coal, okay, has increased very, very significantly in India. What was available at probably 3 rupees and 4 rupees a kg. Today, because to ensure that you get a reasonable steam to fuel ratio in the boilers, most Indian companies are forced to import coal, okay, the entire coal or maybe partially some of the coal from places like Indonesia or South Africa, usually Indonesia. So with this kind of situation, today the cost of coal in many of the process industries in India is somewhere close to about 10 rupees a kg. Okay, which means that the cost of steam uh, is close to about 2 rupees 50 paise, okay, per kg. Okay. And the good old days, we were used to talk about costs which are somewhere close to about 50 paise. Okay, 0.5 rupee. Okay, today we are somewhere near 2.5, if not higher. Okay, and the electricity cost has been more stable. In most of the places, ranges from 7 to about 9 rupees per unit of electricity. Okay, so today, when we look at steam ejectors, though they are very convenient to use, low on maintenance and so on, yet in some cases, revisit is probably called for purely because of the very, very high steam cost. Liquid ring vacuum pumps uh, typically have lower energy costs compared to ejectors. Okay, they need not have to be installed at a high elevation. I'll just go back to the previous slide to just explain that. Now, in steam ejectors, as I just mentioned, now you have condensers where the steam is condensed. Okay, and the condensate has to be collected in a tank or a receiver. Okay, now it is also essential that the receiver is located at least about 11 meters below the condenser. Okay, this is because, again, because the atmospheric pressure. Okay, and who was it, Galileo found out in 1500s that, okay, 10 meters of water column, one atmospheric pressure is equivalent to 10 meters of water column. So because the condensate which is collected in the condenser is at the same vacuum level, okay, this condensate will go down only by gravity. Okay, now to ensure that it goes down by gravity, you have to ensure that sufficient static head is available, okay, which can overcome the atmospheric pressure from whatever is the vacuum pressure there. Okay, so approximately at least about 11 meters would be required, by which the condensate can flow down by gravity. Otherwise, the condensate will tend to accumulate in the condenser itself and slowly start drowning the tubes. Okay, and as you know that if the tubes, if the condensate starts drowning the tubes, then effectively heat transfer area is lost, and the effectiveness of the condenser will be poorer, which will in turn affect the vacuum level. Okay, and can have disastrous consequences. So steam ejectors have this issue of height. Okay, they have to be located at a height. That problem is not there with liquid ring vacuum pumps. Liquid ring vacuum pumps may not need a condenser because the water seal, okay, or the liquid piston itself will be able to absorb good amount of heat. Okay, in some cases where very high latent heat is there, maybe one may have to put a condenser upstream of the liquid ring vacuum pump. Depends on the process. Okay. Uh, it has got higher capital cost compared to the ejector. Okay, it requires more attention in terms of maintenance and upkeep. Yet it is like a centrifugal pump. Okay, the upkeep is required because often the gases which are being evacuated are they end up dirtying the steel water, which also is continuously being cooled. Okay, and if sufficient makeup is not being provided and the too much of dirty water accumulates, it may lead to settlement and certain deposition within the pumps, which eventually end up affecting the performance of the pump. One drawback of this liquid ring vacuum pump is that the operating pressure is limited by the boiling point of the liquid which you're using. If you're using water, as you know, that since it is working under vacuum, okay, one needs to keep the water temperature somewhere close to about 30 degrees centigrade. Okay, if the temperature goes above 30, okay, then the evacuation capacity of the pump drops, because water itself, the water seal itself starts evaporating. Okay, and if the evaporation takes, the seal itself starts evaporating, then the amount of volume available for evacuating the gases from the vessel reduces. So the capacity goes down. So cooling of the water sealant or the water piston, okay, or oil piston, whatever is the media which is being used as the liquid, is also very, very important. Okay, in the case of oil, etc., because the boiling point is high, the chances of the drop in evacuation capacity is less compared to that with water. Now, let us, as I told you, that in energy audits, often people tell us that the steam consumption has been increasing. They tell us, look at the steam distribution system. Is our insulation okay? Okay, are our steam traps working properly? These kinds of issues are often raised when we go for energy audits. Okay. When, if we find that there are large number of steam ejectors being used for vacuum in the plant, we often ask our clients to look at the performance of those ejectors, not from the viewpoint of whether it is giving satisfactory vacuum or not. That usually is the case, because otherwise the process doesn't work. Whether the steam consumption is within limits. And unfortunately, that is where the problem comes, because rarely will you find a steam flow meter on a steam ejector, or probably even a battery of steam ejectors. Okay, so often that information is not available. And when people say that their steam consumption has suddenly increased, okay, and gone uh, beyond their usual norms, okay, let's say 5% increase in the steam consumption, 10%. Very often, when involved detailed studies have been done, these have finally been traced to steam ejectors which are taking much more steam than what is specified. And that is because of the wear out of the nozzles. Because at the nozzle, the steam is expanding to a very high velocity. It's coming at a low velocity, expanding to a very high velocity. So wear out of the nozzles in steam ejectors is a problem area. Okay. And if these nozzles are not checked and replaced timely, you can have a situation that, okay, your system is working fine from the process viewpoint because the vacuum is being attained, but it is happening with phenomenally higher steam consumption. Okay, it is like the usual commonly issue with compressed air leakage. Okay, is often a troublesome issue in most plants. Okay, there's something similar to that. Only thing is, this is linked with a particular device or an equipment. Okay, which is slightly difficult to monitor on a continuous basis. So one of the things which we advise is that in these plants, whenever the plant shutdown is taken, etc., these so-called rugged devices, which often they say don't require attention at all, they've been working for the past 20 years, well, we say open it up, check whether the dimensions are still the same, and whether nozzles have to be replaced, etc., so that one can keep our steam costs under control. Now, for thermal power plants, okay, wherever there's a steam turbine, okay, it can be a condensing steam turbine, or it can be an extraction condensing turbine, where some of the steam is partially expanded in the turbine, then used at a lower pressure for process applications, and some of the steam goes all the way to the condenser. So wherever you have a condensing steam turbine, okay, where all the steam is condensed or some amount of steam is condensed, the vacuum in the condenser is again maintained, okay, by ensuring that the non-condensable gases, or where most of the condensation which is taking place in the condenser of a steam turbine is steam, but the steam also comes with some non-condensables, that is air which has got entrapped in steam. Okay, now this air has to be evacuated to ensure that the vacuum is maintained. Usually most condensing steam turbines are designed for a vacuum pressure of minus 0.92 kg per centimeter square gauge. Okay. And practically, you will find them operating at 0.8, minus 0.88, minus 0.89, and so on. Now, to evacuate, normally in most of the large power plants, liquid ring vacuum pumps are used for evacuating the non-condensables from the condenser of the steam turbine. But in many process plants, okay, chemical process plants, petrochemicals, etc., because a huge amount of steam anyway is being used for the process, it is very common to see steam ejectors being used as turbine on the turbine condensers. Okay. Now, as I mentioned, steam ejectors are the most inefficient kind of vacuum system. Okay. If you replace a steam ejector with a liquid ring vacuum pump, the savings are very, very phenomenal. Now, here is a quick calculation. Okay. Now, suppose you have a turbine where about 1.5 tons per hour steam is being consumed. Okay. Usually, these are consumed at a pressure above 9 kg per centimeter square gauge. So, here is an example where about 9.5 kg per centimeter square gauge, about 1.5 tons of steam is being consumed to maintain the vacuum at minus 0.92 kg per centimeter square gauge. Okay. The same application can be satisfied with a 100 kilowatt water ring vacuum pump, and this 100 kilowatt is electrical power. Okay. Now, today in a cogeneration plant, okay, or even in a captive power plant, where you're getting coal at a price of about 10 per kg, okay, and if one is working at a steam to fuel ratio of about 4.5 to 5, okay, our steam cost would be about 2 rupees 50 paise per kg. Okay. And in the same plant, okay, the electricity price, okay, coming from purely condensing steam would be somewhere close to about 11.5 rupees per kilowatt hour. Okay. Quite high. Okay. But even with this high electricity price, if you substitute a steam ejector with a vacuum pump which is being driven with electricity at 11 rupees 50 paise per unit, and you're substituting steam at 2 rupees 50 paise for the ejector, still the cost saving would be somewhere in the vicinity of 2 crores, okay, which is 20 million Indian rupees per annum. Okay. So, as I told you, proving things by direct measurement is very, very difficult because instrumentation is not there. Even the case studies which exist, it's very difficult to prove everything with measurement. But once we make an apple to apple comparison of equipment which can do the same job, okay, provide the same amount of evacuation and also maintain the same amount of vacuum pressure, okay, the cost savings speak. So this is one particular case study. Okay, so in applications where you can replace a steam ejector either with a water jet ejector or a liquid ring vacuum pump, the savings are immense. If you are able to replace it with the other kind of vacuum pumps, okay, like the screw pump and the claw pump, savings will be much larger. Okay, but for some of these applications where the evacuations of requirements are very large, probably screw pumps and claw pumps today may not be available in those kind of capacities. So today possibly one cannot do that. Okay, but substituting steam ejectors with water jet ejectors or liquid ring vacuum pumps certainly is a possibility. And most of the large power plants do come with liquid ring vacuum pumps. They don't experiment with steam ejectors. Okay, it's only in process industries where people have captive power plants where this problem exists. Now, talking about the liquid ring vacuum pumps, okay, especially the watering vacuum pumps. One very important issue, as I mentioned, is that the limitation of this watering vacuum pump or any other fluid, alcohol or whatever else you may use in these liquid ring, which gives the water seal and the liquid piston or the ring which is created. The limitation comes from the temperature. Okay. In the case of water, we would like to keep the temperature somewhere close to 30 degrees or lower. Okay. Once it goes higher, okay, water starts evaporating at the low pressure which is prevailing in the vacuum pump, and it reduces the capacity of evacuating gases from the vessel which you're trying to evacuate, okay, or the equipment from which you're trying to evacuate the gases. Okay. Now, the paper industry, okay, is one industry which uses large liquid ring vacuum pumps, okay, in the paper for drying off the felt which takes the paper pulp and creates a sheet. Okay. So the felt, which is part of the paper machine, the water is sucked out by a battery of very, very large vacuum pumps, okay, which are usually liquid ring vacuum pumps. And here was a case, this is a practical case which we saw in one of our studies, that the temperature of the water seal or the liquid piston in the vacuum pump was at 42 degrees C. This can be measured very easily because continuously water is coming out of the vacuum pump and is getting replenished. Okay. And usually this water is cooled by a cooling tower. Now, because of deficiencies in the cooling tower apparatus, okay, the temperature had risen to 42 degrees C. So here a recommendation was given to augment the cooling tower capacity and also maintain greater cleanliness in the fill of the cooling tower to bring down the temperature from 42 to 32 degrees C. Okay. And when we made the calculations, now these are the curves. Okay. The x-axis is the suction pressure. Okay. Again in torr. Okay. So this is the atmospheric pressure and these are the lower pressures. And this is the temperature of the water in the watering vacuum pump. Now here are the set of curves. Okay. Now you can see over here. Now here you see the temperature factors. Okay. Now and on these curves you see the temperature. Now these are in Fahrenheit. Okay. The data has been taken from a book which is possibly from the US. That's why everything in Fahrenheit. One thing to observe over here is that as the temperature of the water seal increases, okay, the temperature factor becomes lower and lower. And what the temperature factor is, that if the water is maintained at the design temperature, here in this case it is 60 degrees Fahrenheit. Okay, 60 degrees Fahrenheit will, I think, would come to a temperature which is close to about somewhere maybe in the vicinity of 25 degrees centigrade. Okay, the temperature factor will be 1, which means the vacuum pump would give its full capacity. Now, if the temperature keeps on rising, then you have to follow the lower curves for at any pressure. Now, suppose I'm requiring 100 torr, okay, and I'm getting at 60 degree Fahrenheit water temperature, there is no derating of the vacuum pump. If the temperature rises to 68 degrees Fahrenheit, okay, then you can see it is 0.95. If the temperature rises still further, okay, it goes to 0.7 over here, which means the vacuum pump will give only 70% of its design capacity. And what does this mean? You will have to now add more vacuum pumps. You may have to start the spare pump also to ensure that you get the desired vacuum in your system. Okay. So in the paper machine, continuously from the felt, okay, which is a felt belt actually, water is continuously getting evacuated. And as the felt rotates, it again picks up the pulp, creates the the sheet, and again comes back with more water. So continuous water evacuation is required. Now, in this particular case, where almost about 1,000 kilowatts were being consumed in about 5 pumps, okay, of various capacities, okay, we found that one pump which was consuming about 300 kilowatts could be switched off merely by ensuring that the water seal temperature is maintained. Okay, instead of living at 42 degrees centigrade, bring it down to 32 degrees centigrade. So this is another important. It's not only the vacuum pump, but the associated auxiliaries like cooling towers, okay, etc., also have to perform well, because the temperature at which the vacuum pump operates is very, very critical for almost all kinds of vacuum pumps. Okay, to a certain extent, less for the dry vacuum pumps, but for others, it is very, very critically important. Here is a case study of a steam ejector. Excuse me for some of the typos and spelling mistakes, which was working along with a watering vacuum pump for a noodle dryer, okay, the edible noodles, okay. The total system power consumption was 74 kilowatt. As I mentioned, steam ejectors are the worst kind of vacuum pumps from the energy viewpoint, okay, maybe good from other viewpoint of reliability and so on. Replacement of the steam ejector by a water jet ejector, okay, reduced the power by 40 kilowatts, okay, giving a the investment in the water jet system getting paid back in less than 2 years. Slightly more complicated vacuum systems, typically seen in chemical industries and petrochemical industries, okay, where you need low vacuum for some applications. Now, this particular example is from a petroleum refinery, okay, where the overheads from the VDU, okay, which is the vacuum distillation unit, okay, is being sucked by a steam ejector, okay, at a pressure of 35.2 torr, okay, it is low vacuum, okay. This ejector is working in series, okay, it's a multi-stage four stage steam ejector system, okay. So the motive steam is coming at a pressure of 10 bar. Here you can see almost about 4.5 tons of steam is coming into the steam ejector, okay, at a temperature of about 230 degrees C, pressure of 10 bar gauge. This picks up the gases from the VDU and comes into the condenser, okay, where the steam and maybe some condensables from the gases are condensed, and the non-condensables go to the next stage, the second stage, okay. Here, again, medium pressure steam at 10.5 bar, about 1.4 tons is given, okay. And here you can see the pressure here is now about 89 torr, okay, over here, okay. The gases are now coming at 89 torr over here, okay. The amount of non-condensables coming is about 1.3 tons is coming in here, okay. What was evacuated from here, you can see, was about 10 tons of material from the VDU, okay. What is now coming here is only 1.3 tons, which means the rest of it has got condensed in this condenser along with steam. This is taken forward to the next condenser, okay. Here again, the same process repeats. Steam and whatever else may be left behind to get condensed gets condensed. Now, from 1.3 tons, what is going to the next stage is 0.95 tons of non-condensable gases. Again, some traces of condensables may be there in it. Here, about 1.16 tons of steam is being given in. Okay, again at 10.5 bar. It passes through the condenser. And finally, you can see over here, about 0.784 tons of non-condensable gases are coming into the last stage. Okay, again with some traces of condensables. Finally, it passes through the condenser. Here you can see about 0.75 tons of steam has been given in. So the steam gets condensed, some traces of vapor gets condensed, and then the non-condensable gases, which has not got condensed here, about 0.75 tons of non-condensable gases. We began with 10 tons, okay. Finally, about 0.75 tons of gases are going in, okay, to a fired heater where probably it is used as a fuel, okay. And if the heater doesn't consume it, it will go to the flare, okay. Now you can see over here, okay, one of the major utilities used here is cooling water. You can see over here that about 1100 meter cube, okay, of 1100 meter cube of water is being used for cooling these condensers, okay. So in the it is coming at 32 degrees C, getting heated to 38, okay, and this water is then used in the other condensers, okay, where it gets heated up to 41 and then goes to the cooling tower. So there's a cooling tower system also working along with it. So here you can see that with such a huge amount of steam being used, okay, along with process vapors, where again a lot of the process gases also condense. So the latent heat of those gases also coming into play, okay, which cannot be avoided, which anyway have to be condensed, okay, in the system. But the problem here is a huge amount of steam is coming in, which is the motive fluid, and that steam also has to be condensed, okay. Now in this system, okay, if these two steam ejectors, okay, again looking at the vacuum now to achieve 35.2 torr here, okay, you need to have steam ejectors, Okay, you cannot achieve that with liquid ring vacuum pumps. Okay, you need steam ejectors. But from 35 torr, it has come to 89 torr here. Okay, now from 89 torr, okay, finally it is coming here to the third steam ejector at 176 torr. Now 176 torr can definitely is a kind of vacuum level which can be given by a liquid ring vacuum pump. So there is a possibility that both these ejectors can be replaced by a liquid ring vacuum pump. Before we leave the screen, the total amount of steam consumed is about 7.8 tons here. Okay. For the kind of cost which is prevailing in that particular refinery, it is where the cost is about 1 rupee per kg of steam. The cost is about 7,800 per hour, which is being consumed over here. Okay, 1 rupee per kg. Now, if we look at a scenario where these two steam ejectors continue to work, giving you the gases here at 176 torr, from here it is handed over to a liquid ring vacuum pump. The power required for the vacuum pump is only 174 kilowatt. Okay. Now the cost of grid power to be used over here is at about 8 rupees per kilowatt hour. Okay, because the cogeneration of cogeneration plant is a self-regulating plant, so we are making an assumption that any additional electricity demand would have to come from the grid. Okay, which is 8 rupees. Steam cost continues to remain at 1. Now here the steam consumption drops from what was 7.8 tons, it drops to 5.9 tons, roughly about 6,000 rupees per hour being consumed for steam. The power cost is about at 8 rupees, about 1400 rupees, which means you're saving about 500 rupees per hour. Okay, which turns out to be about 4.1 million Indian rupees, or about 41 lakh rupees. Okay, which is quite significant for one system. Okay, in a refinery you'll have many such systems. Okay, a number of steam ejectors in operation in many of the downstream plants all put together. A fairly huge amount of the steam which is generated goes in for steam ejectors. And steam ejectors again have another problem. They increase the amount of effluent which is there in the system, because there are traces of condensed gases in the condensate. The condensate which is there coming from the condensers of a steam ejector is not clean. So usually this condensate cannot be returned to the boiler. Okay, they have to go to a polishing plant. Okay, where again there is energy consumed, there are chemicals consumed for polishing that condensate. And sometimes in some cases the condensate is so dirty that it does not make sense to send it to the polishing plant. It goes to the effluent plant for treatment and further discharge or reuse. Okay, so again you have energy consumption taking place. So some of these uh, energy guzzling equipments not only end up consuming energy in the device itself, they create issues which lead to energy consumption elsewhere in the system, which also sometimes is very, very significant. I mentioned that the dry screw and the claw vacuum pumps, okay, screw pumps have been in existence for a very, very long time. Okay, but today they're available in larger capacities, and the claw vacuum pumps today are giving the steam ejectors and also the watering vacuum pumps and the water jet ejectors, okay, a run for their money, because now these are available in capacities which are good enough for small processes, not very huge processes, but for smaller processes. Okay, and in a even in large chemical plant or refinery, in the downstream side you have many smaller processes which are working, where again steam ejectors, water ring vacuum pumps, etc. are being used. These can be replaced by dry screw or claw vacuum pumps. And how much can you save? For example, a vacuum ejector consuming 300 kg per hour of steam. Okay, again, assuming that in a chemical plant working with a coal-fired boiler, steam is available at about 2 rupees 50 paise per kg, and the grid electricity is available for 8 rupees. This ejector can be replaced by a claw vacuum pump or a screw vacuum pump consuming about 20 kilowatts. Okay, and assuming now many of these processes may not be working continuously, But assuming it works for 2 shifts at least every day, 16 hours, and it works for at least 250 days out of the 365 days in a year, okay, the energy saving, cost saving potential is somewhere close to about 20 to 25 lakhs per annum. Okay. And considering the cost of a screw vacuum pump or a claw vacuum pump, this investment can be paid back within about 2 years. Okay. So both for large industries and smaller industries, okay, we have opportunities available for savings, which are slightly difficult to detect and quantify very, very clearly because of the lack of instrumentation. But as energy auditors, with the rising cost of steam because of the increasing price of coal, okay, in India especially, and also, and it's true even in Indonesia, okay, we are importing coal from Indonesia, but don't assume that coal in Indonesia is cheap any longer, okay. One of our clients, which had a very large cogeneration plant generating about 75 megawatts of power, okay, which was running as a full-fledged cogeneration plant, okay, has been forced today to work with only at a partial level and take energy from the grid, okay, in Indonesia because of the rising cost of coal, okay. Some of our clients in Europe are also now facing the crunch, especially after the Ukraine war, okay, and Russia throttling the gas supplies from Siberia to Europe, okay. Some of the plants in Germany, especially, are struggling today because of insufficient gas being available, the cost of gas being very high, and today they are probably looking at some of these opportunities which they earlier would never have looked at, saying that okay, steam ejectors are very reliable, we would never like to have a nuisance and increase maintenance and things like that. Today are willing to relook at some of these options, not only ejectors, many other opportunities which normally when the prices are low one tends to overlook and prefer to have a reliable system and a good night's sleep rather than work harder on the maintenance and work with lower energy costs. So these are some of the examples I've given with the brief on the vacuum system. I hope I've been audible throughout. Okay, and I hope most of the screens were visible and you have been able to understand most of whatever I tried to say. Now I would leave the floor open for any thoughts that you may have to share, any comments that you may have, any queries that you may have, and also most welcome, please correct any mistakes because I don't claim to be an expert on vacuum. It's only from the energy viewpoint, some thoughts and some measurements and certain recommendations which we have been generating for our clients, which we have shared over here. Okay, and this is a tough area to work in, but I think increasingly getting more and more important. So now I will leave the floor to the
That
audience.
was great, Mr. Parman, and really a very, very valuable insights for this vacuum pumps. And I mean, there is a lot of appreciation that I can see. I mean, clapping hands, and in question answer box also, lot many appreciation is there for this presentation. And so let me go to the question answers that have already been shared. So I think Mr. Shashi Bhushan Agrawal, he has a query. So I'll ask him to speak because that was related to some of the particular slide. So he will be able to explain it better. Yeah.
Okay. Okay. Mr. Shashi.
Mr. Shashi Bhushan.
I can see the question. What flow rate of both cases? I don't know what he's referring to. Which slide?
That's what.
Okay.
That's what.
Okay. Okay. Fine. Okay. When okay.
Yeah. Mr.
Someone said no.
Shashank,
No.
can you
Yeah.
please do? Yes, you are audible.
Yeah, sir, it's a good presentation. Thanks very much for the excellent presentation. But my only question was while comparing the steam ejector and the watering, if it's very difficult to measure the flow, but if we can get some tentative flow rate, then it would have been more precise to take decisions in future.
The thing is, see, but the guiding factor, because measurement of flow, nobody puts a flow meter for measuring the evacuation unless it's a very clean gas. Okay. So basically, the comparison has to be for the same process conditions, whether we are able to achieve the same vacuum level.
Yeah.
Okay. And I understand that there are times when, especially in chemical process plants, the amount of gases being generated from the processes also are not constant. They are highly variable. Okay.
Yeah.
So it becomes a bit of a challenge, especially when you have to select a new pump and size it. Okay. So some analysis and some modeling probably would be required. Okay. For example, that particular case which I shared of that refinery. Okay. These are kind of models which are generated in Aspen HYSYS. Okay. When you're evaluating these kind of systems. So you may probably have to go in for that kind of modeling to be very sure that the new selection is with adequate capacity. And slight oversizing of all these electrical vacuum pumps, electrical motor driven vacuum pumps is quite in order, because using variable speed drives on these pumps is also an energy saving option. Okay. In fact, for liquid ring vacuum pumps, one of the major developments has been low speed liquid ring vacuum pumps. And especially in the paper industry, where they use these pumps in very huge pumps of large capacities, savings have taken place by replacing old pumps with new pumps which have basically been designed at a low speed. Because the thing is that those pumps are so huge that most of the motors may be medium voltage motors. So people, though variable speed drives are available for variable frequency drives are available for medium voltage motors, people are still a bit hesitant because of the high costs, etc., and a fear about the reliability of the IGBTs and all, especially for critical applications. So in these cases, liquid ring vacuum pumps have been specifically been designed of the same capacities as the previous pumps. Okay, except that they are bigger in size and working at lower speeds. And these and operation of at lower speeds automatically has improved the efficiency of these liquid ring vacuum pumps. So both these things are there. So I agree. There are. It's not a very easy game, but yet, in case you are in a quandary, okay, whether you're making a very tight selection for the new pump, okay, oversizing the pump and incorporating a variable frequency drive is one way of circumventing that problem.
Yeah. Thank you very much, sir.
Any other questions? Anything anyone has to share? I'm
Yeah,
very
Mr.
sure.
Prashant Zala, your question, please. I have enabled you to talk. You had raised your hand.
Yes, sir. Very nicely explained about the vacuum system. So, sir, what is the best achievable efficiency in liquid ring pump, and what are the main causes that impact on down the efficiency of that pump?
See, like we say for a pump efficiency, okay, pump efficiency is 80%, 60%, etc. Moment we get into either compressors, okay, vacuum pump is also essentially a compressor, okay. Only thing is the discharge pressure is atmospheric. That's the only difference, okay, and the suction is at a very low pressure, okay. In an air compressor, suction is at atmospheric pressure, and the discharge is at a higher pressure. Now, in all these cases, you can define efficiency, okay. The efficiency can be designed using any of the thermodynamic terms, okay. It can be isothermal efficiency, it can be isentropic efficiency, it can be polytropic efficiency, okay, number, okay, by basing on how much is the theoretical minimum power required for doing the job and actual how much energy or heat rate is being consumed for that particular application. Okay, but since these are slightly confusing, because once you say isothermal, isentropic, etc., okay, the basis for comparison becomes difficult. So in all these cases, the driving number which you have to look at, okay, because the evacuation capacity of a vacuum pump is defined at atmospheric pressure, okay, not at the lower pressure at which it is working. Okay, so with that kind of a scenario, okay, you have to look at whatever is the design energy heat rate in the case of a steam ejector, or power consumption for a liquid, which is the design power, versus the guaranteed evacuation rate at atmospheric pressure. Okay, that is the only thing which we can look at, okay, when you are selecting a new system, okay, or trying to evaluate a system. That becomes a starting point. Then coming to liquid ring vacuum pumps, the most important point which I already mentioned is the temperature of the water seal or the liquid piston. Okay, people call it as a seal. Yes, it does a sealing job, okay, but it's also working as a water piston. And because that water piston is continuously absorbing the mechanical heat of compression, okay, and also whatever condensables which may be coming with the gases which condense at that particular temperature, okay, one has to ensure that the amount of makeup seal water which is given, that rate is at a level by which the internal temperature is maintained, and whatever water is overflowing out of the vacuum pump at a higher temperature, that is getting cooled to a temperature of at least 32 degrees centigrade. Okay, that will ensure that at least the vacuum pump will work at an evacuation rate for which it has been designed. Okay, the second issue is if the gases contain components or constituents or compounds which have a tendency to condense, okay, and also form crystals within the pump itself, then there's a tendency of deposition build up inside the pump. And moment deposition builds up inside, the working volume available in the liquid ring vacuum pump reduces, and that again impacts the evacuation capacity. Okay, so cleanliness of the fluid of the water within the liquid ring vacuum pump, okay, that and the temperature are the issues which you should be looking at to ensure that the system is working efficient.
Thanks, sir.
Yeah, and one more issue, especially in chemical plants, it possibly may also make to put an upstream condenser before the vacuum pump, okay, so that some amount of the condensation of condensables takes place before the vacuum pump itself, okay, and it is removed separately, okay, instead of all the condensables coming to the vacuum pump and leading to deposition within the pump. Some places they do that.
Yeah. Now next, Mr. Dilesh has a question. Mr. Dilesh, can you speak?
Yeah, good evening, sir.
Yes, Mr. Dilesh, we can go on. You can go on.
Yeah, am I audible?
Yes, you are.
Yeah, thank you, sir, for the amazing session. Actually, I started energy management by reading the manuals developed by you. So my question was, sir, I think a lot has been discussed, but are there any specific technical barriers, when we want to replace maybe a four-stage steam jet ejector with a water ejector? You mentioned out some points, but are there some specific technical issues in a chemical plant?
See, the kind of gases which are evacuating, okay, so some of them may be corrosive in nature, okay, some of those gases, no, but usually when you have corrosive gases, even steam becomes steam ejectors also become a problem, okay, to some extent, okay. The issue is that if anything, you're having gases which can either condense out, okay, crystallize, deposit, polymerize, okay, or create severe corrosion in any of the downstream equipments, then that becomes an issue. Okay, so there are some cases where the motive fluid, okay, is not steam. Okay, you may also use some other vaporizing fluid like glycol, okay, which is used, and often in such cases where there are certain very corrosive constituents which have to be removed out of the system, and at times the motive fluid can be some kind of a solvent which has the capacity to dissolve that troublesome component and pull it out of the system and not take it all the way down to the downstream stages, which can create reliability issues. Okay, so the problems are basically related to what kind of a gas or mixture of gases. Usually it is not one gas, it is a mixture of gases which is being evacuated. Okay, so yes, you need to have a proper analysis, okay, and what kind of motive fluid which you're using, etc. Okay, so especially when you are, if it's working well with a steam ejector, okay, and if you're moving for any of the other options, this requires a very, very careful study before you can jump in to the and look for the opportunity purely from the energy saving viewpoint. Okay, it has to be done very, very carefully. So the composition of the gases which are being evacuated, one should have a good idea about what all it may contain, and also especially if the reactors which are from where they are coming are handling different products at different points of time. Okay, then probably you have to look at all the products which are going to be processed in the reactor and be very sure about the composition of the gases which are being evacuated. That I see as the biggest challenge. And in some cases, even in liquid ring vacuum pumps, water is not used, oil is used. With oil, the greatest advantage is that with that you can operate the liquid ring vacuum pump also at a higher temperature to make sure that some of the components of the gas, in case they have to ensure that the temperatures are kept well above the condensation point of those gases. Okay, so that there is no chance of any severe settlement taking place in the vacuum pumps or in any of the associated equipment like the condensers.
Okay. So thank you so much, Mr. Paraman. It was really a great learning session, and I hope everyone will benefit a lot from this session. And I have already shared Mr. Paraman's email address in the chat box, and you can contact him for your further queries. And we hope to keep bringing you such learning sessions and enrich you with knowledge of the energy efficiency. So, thank you so much, Mr. Paraman, for guiding us by this session, conducting this session. Thank you.
Thank you, Bhavna, and the entire management of AE, and all the participants and colleagues who tuned in, okay, and listened to my slightly boring monologue, okay, but I hope some of it was useful.
It was so much useful. I mean, really, it is so much humble of you to give such a vast knowledge and sharing so many case studies also. That was great. Yeah,
fine. So anyway, so I think again to all the participants, I'm always open to sharing and doing loud thinking together. So at any point of time, something crops up on vacuum or anything else, I'm quite happy to discuss. Only always just make a mention where we first interacted. So if you're interacting with me for the first time on this particular platform, just mention it so that I have the background of whatever we are talking about. So thank you very much. I, as usual, enjoyed talking, though I don't like these virtual conferences and meetings a lot, because it's always like talking to a wall. Okay, so when it's talking to a live audience, then so the whole thing is much easier for the faculty, because there's some interaction taking place as we move on, and at least when one says something in a lighter vein, okay, there is some laughter, etc. Here, everyone is muted when the session is going on, so we don't hear much. But anyway, happy to be here. Okay, and thanks Bhavna, Shirish, Milind, everyone for inviting me over. And I'll be happy to contribute in future too. And to everyone else here, some of you would be experts in your own area, okay, much more knowledgeable than me in many of these topics. I think if you have anything to share, I think some of you also can get in touch with Bhavna, and let us also learn from your experience. Thank you very much, and have a good day.
Thanks.